Okay guys, in this video I wanted to discuss weak acids and weak bases. So here I've got a generic weak acid ionization reaction on the slide. This weak acid donates its proton to water. That gives us some hydronium and leaves the conjugate base behind. I've set up an ice table for the problem, so we've got the initial concentration of the acid, the change in the concentration, and the equilibrium concentrations. So the initial concentration of the acid is some value Ca. The initial concentration of hydronium is approximately 0. It's actually 10 to the minus 7 at 25 degrees Celsius, but we can neglect that in this problem. And the initial concentration of the conjugate base we'll assume to be 0 for our purposes here. There will be some dissociation of the acid, so the acid concentration will decrease by some amount x. That will increase the concentration of both the hydronium and the conjugate base by the same amount x. To get the equilibrium concentrations, we add the initial concentrations to the change in the concentrations. That gives us Ca minus x for the weak acid, and just x and x for hydronium and the conjugate base. The Ka expression for this reaction, the equilibrium constant expression for this reaction, I've shown here on this slide a couple slides forward, so I'm going to skip ahead. Here's the expression for Ka. It's defined as the product concentrations over the reactant concentrations, just like any other equilibrium constant, but for acid ionization reactions we call it a Ka. And you'll notice that we did not include the water concentration in the denominator here. That's because water is a pure liquid, and we omit pure liquids and pure solids from our equilibrium constant expressions. The value of Ka tells you something about the strength of the weak acid, the relative strength. And so the larger the Ka value, the more dissociation you're going to see, the more ionization you'll see. So a large Ka value would be a fairly strong weak acid. A small Ka value would be a very weak weak acid. You can look in your textbook. In one of the appendices, there's going to be a list of Ka values for a whole bunch of different weak acids, and you'll have to look up those values for some of your problem solving. A couple things that you can calculate using an ice table. For starters, if you know the value of x, you can calculate the pH of the solution, right? The hydronium concentration at equilibrium is related to the pH, and so given x, you can calculate pH, or as we'll see in the problems in this video, given the pH, you can use that to calculate x. Another thing that you can calculate is the percent ionization of the acid. And so that's defined as the amount of the acid that dissociates divided by the initial concentration of the acid times 100. I'm not going to prove this right now, but the percent ionization of weak acids increases with the value of Ka. In fact, it increases as the square root of Ka. So the larger the value of Ka, the more ionization you will have, and so the greater the percent ionization will be. Conversely, the percent ionization is inversely proportional to the square root of the initial concentration of the acid. So the larger the value of Ca, the smaller the percent ionization will be. In this slide, I just wanted to illustrate that you can do exactly the same thing for weak base ionization reactions. So I've got a generic weak base ionization reaction here. B is our weak base. It accepts a proton from water, giving us its conjugate acid and leaving behind hydroxide. The ice table can be set up in exactly the same way. The Kb expression is analogous as well, and you'll find values for different weak bases listed in the appendix of the textbook. And you can also calculate a percent ionization for a weak base. And the equations, the ice table, they all work in exactly the same way as they do for a weak acid. I wanted to point out another relationship between conjugate acid-base pairs. Specifically, the Ka value for the acid times the Kb value for its conjugate base equals the value of Kw. And I've illustrated how that works on this slide. So consider the generic weak acid ionization reaction that we had before, and this is its Ka expression. Take its conjugate base and write out the base ionization reaction for it. So here, the conjugate base is acting as a base and it accepts a proton from water. That reforms the weak acid and leaves behind hydroxide. And here's the Kb expression for that weak base. If you take these two equations and add them together, these two chemical equations, and add them together, you get the autoionization reaction for water. And that's because the conjugate bases cancel and the weak acids cancel out when you add the two equations together. We've learned previously that if you add two reversible chemical equations together, what you need to do is multiply their equilibrium constants together. And you can show that this relationship is true if you take the product of Ka times Kb explicitly. You'll see that the conjugate base concentrations cancel and the conjugate acid concentrations cancel out as well, leaving you with the ion product for water, which is just Kw. So this relationship holds for any conjugate acid-base pair, and we'll use this equation in our problem solving. So the rest of the slides that I'll present in this video are just problems. And so in our first problem here, we are looking at a solution of nitrous acid, a weak acid, and we're given its initial concentration, and we're being asked to calculate the percent ionization, given that the pH of the solution is 2.09. And so I've written out the ice table for this reaction to illustrate what's going on. So we've got the nitrous acid donates a proton to water. That gives us hydronium and leaves behind nitrite. We know the initial concentration of the acid. And here's the important part, the pH that's given to us in the problem, that refers to the equilibrium concentration of hydronium. So since they've given us the pH, we can use that to find X. And in our percent ionization formula, what we need that value of X divided by the initial concentration of the acid multiplied by 100. So substituting in our expression for the hydronium concentration, then putting in the numbers, gives us that the percent ionization in this case is 6.5%, which means that 6.5% of the nitrous acid is in its ionized form. In this problem, we're asked to use the Ka-Kb relationship for a conjugate acid-base pair. Here they are giving us the Kb value for nitrite, and they're asking us to calculate the Ka value for nitrous acid, its conjugate acid. And so the Ka-Kb relationship is this. We take this equation and solve it for Ka, which is our unknown. That gives us Kw over Kb. Substitute in 10 to the minus 14 for Kw, substitute in the value that's given to us for Kb, and that gives us the Ka value. In this problem, it's a little bit different. What they're asking us to do is to calculate the Ka value for a weak acid, acetic acid, given the equilibrium concentrations of acetic acid, hydronium, and acetate. So here is the acid ionization reaction for acetate, for acetic acid. Acetic acid donates a proton to water. That gives us hydronium and leaves behind acetate. Here's the Ka expression for this weak acid ionization. You substitute in the equilibrium concentrations given, and that gives you the Ka value, 4.12 times 10 to the minus 5th in this case. This problem is identical to the last one, so I'll leave it to you as an exercise. Here we have an illustration that the types of problems that we've been looking at can also be solved for base ionization reactions. So caffeine is a weak base. They want us to calculate the Kb for caffeine given the equilibrium concentrations of all the species that participate in the base ionization reaction. So here, caffeine acts as a base. It accepts a proton from water. That gives us its conjugate acid and leaves behind hydroxide. We set up the Kb expression for caffeine, substitute in the equilibrium concentrations, and that gives us the value of Kb, 2.5 times 10 to the minus 4 in this case. This problem is identical to the previous one, so I'll leave this as an example for you guys to work out on your own. This problem is a bit of a hybrid between the last two problems that we've looked at. And so here we're considering nitrous acid again, and they tell us the initial concentration of the acid in the solution, and then they give us the pH of the solution. But they want us to calculate the Ka, not the percent ionization. So I've written out the ICE table again to illustrate what's going on. So we have the acid ionization reaction. We know the initial concentration of the acid, and the pH tells us what the equilibrium concentration of hydronium is. So we know the value of X. If we know the value of X, we can calculate the hydronium concentration, we can calculate the nitrite concentration, and then we can use the value of X together with the value of Ca to determine the equilibrium nitrous acid solution. So this first line here, what I'm doing is I'm calculating the value of X from the pH. You get this concentration. Then you take that value of X and substitute it into this expression for the equilibrium concentration of nitrous acid. And that gives you that value right there. You then take these two numbers, substitute them into the Ka expression for nitrous acid, and it gives you the value of Ka. Okay, so we'll stop this video here and we'll pick up on this slide in the next one.